All right, y'all. So this is 13.5 continued. I think this is video 8. I have found out a way to sort of hack the noise from the pen, and so this should be a little better than the last video. So, all right, carrying on with the TNB frame. What we want to think about now is, here's a question. How does the derivative of this B vector with respect to S relate to the TNB frame, right? Which is what we did with the last sort of last stuff. So here we go. Let's do some chain rule fun here. So dB ds. This is the derivative with respect to S of the vector B, which is the derivative with respect to S of the cross product of T and N, because that's how B is defined. And this is, when you use those properties, it's dt ds cross N plus T cross dN ds. Right, so we've used the rules of cross products, and which looks like the product rule. Okay, so this is key. Go away. Auto minimize. This is key. Damn it. All right, this is key. N, the vector N, is in the same direction as the derivative of T with respect to S, right? Which brings it inward. So dt ds and N are parallel, hence dt ds cross N is equal to the 0 vector. That's because these two guys are parallel. Okay. So this guy equals 0. So now the derivative with respect to S of B is just this. So we have dB ds equals T cross dN ds. Those are all vectors. Okay. But the derivative of here, I'm trying to make this. So the derivative of dB ds is orthogonal to T. So the derivative of B with respect to S is orthogonal to D. So dB ds is orthogonal. So dB ds is orthogonal to the plane of B and T. which is called the rectifying plane. Or in other words, the BDS is parallel to N. Okay? Okay, that's a lot to take in. So the takeaway here is that dBds is parallel to N. And this says then, oops, here I can do this. This says that dBds is a scalar multiple of N because they're parallel to each other. And the scalar multiple we use with a negative in front is tau. Okay? So this says dBds, the derivative of b with respect to s, is equal to minus tau times n, scalar multiple. And this negative out in front here is traditional. So in other words, if tau is negative, then this whole term is positive. And if tau is positive, this thing's negative. It's just the way it's done, so we're going to stick with tradition. And this number, tau, is known as the torsion, which is the amount of twist, right? And so tau is equal to minus dB ds dotted with n. And this is a dot product. It's a scalar. Okay. All right, and furthermore, oops, wrong size there, here we go. Torsion is the rate at which the oscillatory plane, and this is the plane made by cap t and cap n, the vectors, the rate at which this plane turns around about t. Okay, and so when we meet, I'll give you some visuals. So in class, about what I mean at the way tau moves about the oscillatory plane, how it moves about this vector t. All right, so this one's a shorty, and so we can have a big chat tomorrow, being a Friday. And so here's the rest of the homework. I think this is homework 4, section 13.5, 2, 7, 11, 13, and 26. So let's have a bit of fun here. Happy. I'm going to run out of space. Hold on, let me make it small. Happy. Oops. Happy Friday.